Hello. Okay, so I'm going to start now. Today we're going to talk about a bunch of really practical issues that we see in Bitcoin and also in Bitcoin-like blockchains. So one point I have to mention before I start is that in this module of the course, I don't exactly follow Bitcoin. So some of the things that I say do not really match with Bitcoin in practice, but I keep the main high-level ideas the same. So I have already simplified a lot of things in how Bitcoin works. Okay, with that being said, let me start. Okay, so the first problem I want to talk to you about today is the amount of time it takes for a transaction. And what do I mean by that? Well, let's consider our usual scenarios. So let's say this is my scenario. Let's say that Alice wants to buy something from Bob, and let's say it's a physical thing. For example, let's say she wants to buy a bag of chips, maybe. So I don't care what it is exactly. The only thing that I care about is that it's not something on the blockchain. So it's something in the physical world. And Alice wants to buy it from Bob. Okay. And of course, the payment is supposed to be on the blockchain. So if you have a scenario like this, we already know that Alice should create a transaction that pays the money to Bob. So the steps are quite easy. The first step is that Bob tells Alice about his address or his public key. So I'm just going to write address now because we are already used to this, using public keys as addresses. And then the second step is that Alice creates a transaction. So let's call this address the address of Bob. So I write it like that. And then Alice creates a transaction Oh, okay. Let me stop the sharing and share again just to make sure everyone can see it. Okay, hopefully this should work now. Okay. So in the first step, Bob tells Alice about his address. He tells, send the money to this particular address. And then in the second step, Alice creates a transaction. Let's call that TX that pays this particular address that was given to her. So the idea is that, again, as in our previous cases, this is a transaction. It has a bunch of inputs. These are probably coins that belong to Alice. And it also has a bunch of outputs. Maybe Alice is doing something else in this transaction as well. Maybe she's sending some of the money back to herself. But what we care about is that there is an output that is paying to this address of Bob. And of course, they also agree about the price. So it's paying the amount that Bob has asked. Okay. Now, what is the third step? Well, this transaction has to go on the blockchain. So someone has to publish this. And it doesn't matter who publishes it. Maybe Alice publishes it on the network, maybe Bob does it. But of course, Alice has to send it to Bob so that Bob knows what transaction he has to wait for. So let's say that Alice sends this transaction to Bob. And let's just assume that Bob publishes the transaction. Okay, so Bob publishes this transaction on the net. Now, the main question I want you to consider is, after all of this is done, how long should Bob wait before he can trust that this transaction has gone through and before he can give the bag of chips to Alice? Okay. So we already know that a transaction that is just announced on the network is almost worthless, right? Because it just goes through that propagation protocol and a lot of people hear about it, but all the nodes that hear about it will just put it in their mempool. And the transaction is not really done until it is on the blockchain. So there is a question here, why does Alice need to send a transaction to Bob and not just publish on the network? It doesn't matter. Alice can also publish it on the network. So in steps 3 and 4, what I care about is that, well, the transaction gets published on the network and also Bob knows which transaction this is. So you can do it in any order you like. But let's say we do it in this particular order because it makes things easier to speak about. Okay. So the problem is that this transaction is now published on the network, but there is nothing that stops Alice from doing double spending, right? So let's consider the simplest case here. Let's say this transaction had exactly one input and one output. And so the idea here was that it took some money that belonged to the address of Alice and sent it to the address of Bob, right? So as we've seen before, what Alice can do is that she can create another transaction that uses the exact same coin that was used here, and sends it back to herself or sends it to someone else other than Bob. And this was what we called a double spending attack. And now the problem is that Bob has no way of being sure that this particular transaction gets on the blockchain and not the other transaction that Alice created in her double spending attack. Actually, Bob cannot even be sure if Alice has done a double spending attack or not. Okay, so this is the first problem. Alice might spend. Let's give this coin a name. Let's call this coin C1. So C1 was the output or the coin that Alice used in this transaction and sent the money to Bob. Maybe Alice creates another transaction exactly in the same way that uses the same C1 that used to belong to one of her addresses and pays it back to herself. Okay, so we call this one the second transaction or transaction prime. Okay, and if Alice does this, then Alice can publish this transaction. So let's say Alice publishes TX prime on the network. And now there are two problems for Bob. So maybe I can write it like this. Problem 1.1 for Bob is how to detect this kind of attack. So if Alice does this kind of double spending, how is Bob to know? And the next sub-problem, let's call it problem 1.2, is how to be sure that the original transaction gets on the chain and not the double spending transaction. So how to ensure TX is processed and not. Okay. So the first problem is kind of easy. What Bob can do is that he can have a lot of nodes, and maybe he can put the nodes on different places in the network. Again, maybe one node on each continent. So that if Alice tries to do double spending, Bob would also see the other transaction. So you see the problem with just having one node is that suppose Bob has only one node, and suppose this node is in Hong Kong, maybe Alice publishes the double spend transaction somewhere else. Maybe she publishes it in the US, and then maybe it doesn't make it to the part of network that Bob is located. Okay, so if I just want to show it a bit pictorially, suppose that this is where Bob is, this is Bob's node, and let's say that Alice double spends here. And by double spending here, I mean that she publishes this other transaction here. Now, of course, we saw the protocol that we have for propagating these transactions. So what would happen is that the nodes that are generally closer to the double spend will consider that the double spend happened first, and the nodes that are generally closer to Bob will suppose that the original transaction happened first. So these nodes will consider the original transaction to be valid, and they will reject the double spend transaction and say, okay, this is a double spend because we've already seen another transaction that uses the same coin. So they will only have the original transaction in their mempool. But here, the other group will only have the double spend transaction in their mempool. So these guys will think that TX prime, the transaction that pays the money back to Alice, is valid. And you see the problem is that if Bob has only one node, he might never hear about TX prime. Because what happens at the boundary of these two groups is that, well, there is a node here that first heard about TX prime, and there was a node here that first heard about TX. So this node that heard about TX prime tells all of its neighbors, hey, I know this new transaction TX prime, maybe he's a neighbor with this TX node. But when this happens, this TX node would just ignore the information about TX prime, because that was what we were doing when we were checking that the transactions are valid. If this node already has seen TX, they will just say, okay, TX prime is double spent, so it's invalid, and I will not propagate it any further. So what would happen here is that only the nodes that are on the boundary, only the nodes that are in this first group that think TX is valid, but have some connection to a node that thinks TX prime is valid, only those nodes will hear about TX prime. And of course, on the other side, only the nodes that are on the boundary will hear about TX. And now if Bob is unlucky, and if his node is not on the boundary at all, which is a very likely occurrence if you only have one Bitcoin node, then what would happen is that he will only see TX, and he will think that all of his neighbors only know about TX. He thinks that TX is the only transaction that is using that particular coin on the blockchain. And he will not know that Alice is doing a double spending attack. But of course, the problem is that later on, maybe it happens that the miner who mines the next block is here. Or for some reason, even if the miner has heard of both transactions, maybe the miner prefers the second transaction because, let's say, Alice is malicious and this one pays a larger transaction fee than the original transaction. So the miners prefer this one. And so it might be the case that the miner is in the camp that prefer TX prime, and they will put TX prime into the blockchain. And so Bob has seen this transaction TX, and if he has already given away the physical good, then he will later on be very disappointed to see that actually TX prime gets on the chain and TX becomes invalid. Okay? And of course, as I said, the easy solution to this for Bob is to just deploy a lot of different nodes at different parts of the blockchain, at different parts of the network, sorry. So if Bob has a node here, one here, and so on, then it is very likely that Bob will hear about the other transaction that is doing the double spending. And as soon as he hears about the other transaction, well, Bob can say, okay, I'm not going to give you the bag of chips. I'm going to wait until I see which transaction gets on the blockchain. Okay. So the answer to how to detect double spending is to deploy many nodes, or let's say several nodes, in different locations. Okay. Now, the next problem is, how do I ensure that the original transaction is processed and not the other transaction? Well, there is nothing Bob can do about this, right? Because the miners are the ones who decide which transaction gets into a block and which transaction gets added to the blockchain. So the only thing that Bob can do in this scenario is to wait. So he waits until one of the transactions gets on the blockchain. And when one of the transactions get on the blockchain, then he can just check, was it the right transaction? Was it the transaction that paid me, or was it the double spend transaction? If it was the transaction that actually paid Bob, then Bob can give the bag of chips to Alice. Okay? So this basically means that if you are a seller that is using blockchain, you have no choice but to have a lot of different nodes in different places. Okay. Yeah, and this is also in the chat. But now there is an even deeper problem here. So this is the second problem that Bob will have. So suppose that the right transaction has gotten on the chain. So this is problem 2. Let's say that we assume TX is mined in a block and added to the consensus chain. Can Bob be sure that he's paid? Well, actually, not really. And the problem is, what if a fork happens? So again, let's go back to our blockchain now. So let's say that this is my blockchain. So this is a linked list of blocks, and each block has a hash pointer to the previous one. And let's say that the transaction that paid Bob is in this block. So let's say that transaction is somewhere here. Okay, so it has gotten into the blockchain. A miner has mined it. They have solved the proof of work and everything. or in other words, Bob has waited here until the right transaction is put into the blockchain. But of course, the problem is that it might be the case that at around the same time, another miner finds another block that doesn't have this transaction, or maybe even has the other transaction in it. Who knows? And now there's a fork in the chain. And as we said before, the longest chain is the consensus chain. So it might be the case that later on this one gets longer, right? And if this one gets longer, then basically, as we said before, since the longest chain, which is now this one, since the longest chain, which is now this one, is the consensus chain, that means that this one will be completely ignored, right? So the problem that Bob has is that he has to wait until he can be sure that there will be no such fork, no fork that basically removes this particular transaction from the chain. And of course, he can never be 100% sure, because as we saw in the previous session, if there is a miner who controls more than 50% of the total hash rate, or a series or a group of miners who do that, at the moment there are 4 miners that have more than 50%, they can basically fork the chain at any point. So they can say, I want to fork it from here or from here. So there is no way to be 100% sure that the chain will not fork and that transaction will always remain. But here's the thing, we don't need 100% certainty. What we need is certainty with very high probability. So how can Bob know with high probability that TX stays on the consensus chain? Or actually, instead of just saying TX, let's say that TX was in a block B. How can Bob know with high probability that B stays in the consensus chain? Well, let's just look at the same picture as before. Let's say this is again our blockchain. And let's say this is the block B that has the transaction that Bob cares about. So it has TX in it. And we want to make sure with a good probability that B will not be lost in a fork. Well, what Bob can do is that he can just wait a bit more until there are more blocks added to the end of B, okay? And the more blocks are added, the harder it gets to create a fork that doesn't include B. Because now if someone wants to do a fork that doesn't include B, they have to start from here or somewhere further back. And they have to create the longest chain. So they have to, in this case, generate 5 valid blocks. They have to solve 5 proofs of work, which is quite hard. And the more Bob waits, the more security he has. So if he waits for just 1 block, there is already a good chance that it will not be reverted. But if he waits for 10 blocks or 100 blocks, then the probability that it gets reverted and forked is much less. Okay? So these blocks that are added after this particular block will be called confirmation blocks. So we call these confirmation blocks or just confirmations. And this is because their existence confirms that this block is going to stay in the consensus chain and increases the probability that this block stays in the consensus chain. Okay? So from the early days of Bitcoin, one of the rules of thumb that I don't know who invented, but everyone goes with, is to wait for 6 confirmations. Oh, and some people actually also count B itself as a confirmation. So that's questionable. Maybe B is a confirmation, maybe it's not, but anyway. So most people decide to wait for 6 confirmations. And if they wait for 6 confirmations, that means that, well, as we said before, every block is added roughly in a 10-minute interval from the previous one. So depending on how you define a confirmation, it will take either around 60 minutes or 70 minutes for one transaction to be secure, and for Bob to be 100%, well, not 100%, but close to 100% sure that this transaction will not be reverted and that he can give the physical good to Alice. So around an hour. Okay. So this is the situation that we have here. And of course, this is not ideal, because if you want to buy something, if you want to, for example, buy a coffee, or if you want to buy from a vending machine, you don't want to wait an hour for so many confirmations, right? This might make sense if you're buying something really valuable. So if you're buying, let's say, a laptop or something that is worth at least a couple of $1,000, or in case of Hong Kong, maybe tens of thousands of dollars, then it makes sense to wait for 6 confirmations. But in the real world, if you want to just buy something small, this doesn't make much sense, right? You don't want to wait for an hour when you have other alternatives. For example, you have credit cards or payment apps that work basically instantly. So is this an overkill? Can Bob give up earlier? And the answer is actually yes. So here's the thing. First of all, you don't need to wait for so many confirmations. Waiting for 6 confirmations is an old relic from a time where Bitcoin miners had much lower hash rates and forks were much more common than now. So nowadays, this is kind of historical. No one really wants to wait for 6 confirmations, even though still a lot of people just go with the rule of thumb. But actually, as soon as the transaction is on the blockchain, Bob can be pretty sure that that transaction is fine. Like it's there's a very low chance that it gets forked. And especially if you're talking about a bag of chips or something that has very low value, it doesn't make sense to wait so long. You can just trust the customer at that point and say, okay, this is fine. Okay, but there's also another way that Bob can defend against such attacks. Well, we talked here about how Bob can detect them, right? So if Bob has a good enough detection mechanism, if Bob has a good distribution of nodes around the network, then Bob can see the double spend. So he can just trust his nodes and he can say, okay, whenever Alice comes to buy something, if I detect a double spend in, let's say, 10 seconds, then I will say, okay, you're double spending, you're a dishonest person, so I'm going to wait for maybe 6 confirmations. But if after 10 seconds he didn't detect a double spend, then there is no point in waiting. That's the transaction that exists. Bob could check that the transaction was valid, and it is very likely that this valid transaction will be added to the chain. So Bob can just say, okay, I'm sure that you're not double spending with a good probability because I have a lot of nodes and I'm not seeing any double spending. So here's your bag of chips. But there is an even stronger thing that Bob can do. And this is why I said here that Bob publishes the transaction on the network. So I was getting ready for this thing here. So after Alice sends the transaction to Bob, what Bob can do is that he can publish this transaction on the network from all of his nodes. Okay? So if, again, Bob has a lot of nodes that are strategically placed so that they're close to everyone in the network, and if Bob suddenly announces this particular transaction from all of his nodes, then it is very likely that the whole network will only just hear about this transaction and will consider the second transaction as invalid. So this is the combination of strategies that Bob can do, and generally it all depends on having a lot of nodes and having them at different parts of the network. So if you have a lot of nodes, it's easier to detect if someone is doing double spending. It's also easier to publish a transaction that you want to get to the whole network. So if, well, I don't know if you've seen any of these. Actually, I think they exist in Hong Kong. There are vending machines that use Bitcoin. Right? And especially when Bitcoin was cheaper, it made more sense to have vending machines that used Bitcoin. And basically what they did was that they had a lot of nodes. So you paid in Bitcoin and they worked instantly because they could just get this transaction and they could publish it around the network all over the world, and they could be reasonably sure that you cannot double spend it. And because you couldn't double spend it, it was as good as being on the blockchain. Of course, it took 10 minutes for it to get on the blockchain. And then, of course, if they wanted to wait for confirmations, it would take an hour. But in practice, that was good enough. And most people cannot really do any kind of double spending if you have enough nodes on the network. Okay. So let me just go and answer the questions before continuing. Okay, so there's a question, how long is the waiting time in real life? As I said, if you want to be really, really sure, you can wait an hour. But in practice, if you have many nodes, you can do it instantly, and it's safe enough. Okay. So another question is, if Bob's transaction is ignored due to a fork, would he have to send the transaction again? Yes and no. So it depends on what happens in the fork. So let's say I have, okay, let me just draw this again. So let's say this is my blockchain. And let's say that this is the block B that contained the transaction TX that Bob cared about, right? So it might be that there is another block here and there was a fork. This block does not contain TX. And so it might be that then this one gets longer and TX is not on the consensus chain anymore. But if this happens, Bob doesn't have to publish TX anymore. TX will remain in everyone's mempools, including the miners. So it might be the case that in the next block, or maybe even in the block after the next, a miner adds TX, maybe here or here. So in this case, it's just more waiting for Bob, right? But he doesn't have to announce it again, of course, because if the whole network has heard about TX, they have heard about TX. There's no point in announcing it again. It will mostly be ignored. Because again, if you think about how propagation worked, when as a normal node, you receive a transaction, you propagate it only if it's valid and only if it's new. So if you've seen this transaction before and Bob tells you about it again, you will just ignore it and it will not be propagated again. But a worst scenario is this. Suppose that Alice has done double spending. So suppose that we have these two transactions, TX and TX prime, that use the same coin, and one of them pays it to Bob, the other one pays it back to Alice. And now suppose that there is a fork and the other block in the fork contains TX prime. Okay? So if this happens, and then if Bob gets unlucky and this block gets into the consensus chain, so if this side gets longer, then what happens is that since TX and TX prime were using the same coin, and since TX prime got into the consensus chain, TX is now an invalid transaction. So that transaction is just gone, and announcing it again will have no effect because it's an invalid transaction and it will never be mined or added to the consensus chain ever again. So I guess actually the answer to your particular question would be no, because in any case, Bob has no reason to announce the transaction again. Yeah. Okay. Okay, so another question is, what happens if another fork becomes consensus? Alice's money just disappears? Well, in this case, we're talking about Bob's money. So yes, Bob's money will just disappear because the transaction that paid that money to Bob is no longer on the consensus chain. So that means that that transaction effectively doesn't exist. Okay. So another question is, how does the hash rate affect the time we have to wait before being sure? Well, it has a minor effect on it, but not that huge of an effect, because on average, a block is mined every, let's say, 9 to 11 minutes based on how long we are after the last difficulty adjustment. So if you have to wait for, let's say, 6 blocks and each block is coming every 9 minutes, you have to wait less than if the blocks come every 11 minutes. But on average, it's going to be close to 10 minutes per block. Okay. So another question is, what if Alice herself is a miner and she can process TX prime herself? This is actually a great question. So in that case, there is nothing Bob can do against this, but it's very unlikely that a particular miner can be sure that she gets to add the next block, right? So if Alice is the miner, you have to think about the proportion of hash power, of computational power that Alice has, right? And it's very unlikely that that's a huge proportion. So the chances of Alice in adding the next block are really slim. So I don't think Alice would be able to do this kind of attack. Okay. And of course, there is also the answer here that if that happens, well, Bob has to wait for just one block, right? So he waits for one block, and if he sees that Alice is doing this kind of attack, he just says, I don't give you the chips. But the downside here is that, again, he has to wait for roughly 10 minutes. And that's still not good enough. So if you want to have, let's say, almost instant payments and almost instant delivery, for example, in a vending machine, then Bob just has to accept these kinds of risks. But this is a really small risk. Again, I have to repeat this, that any particular miner has a very small stake. It has a very small proportion of the total hash power. So it's very unlikely that Alice can do this kind of attack. Okay. So another question is, can the malicious party create a cluster of many nodes in a single location to prevent others from detecting double spend in that location? That's actually an interesting question. I don't know, because, well, how can you, it's probably hard to prevent others from connecting to other, from connecting to nodes that are very distant from them. So this is more of a networking issue. And honestly, my background is not in networking, so I can't really give a good answer to this one, sorry. But what I can be sure about is that if you deploy your nodes as Bob in many different places, then Aleph cannot fool you into thinking that she's not doing double spending when she is. Okay. So this was the main problem I wanted to talk about today. But I just want to tell you a tiny detail that I overlooked before. And this is because this detail matters a lot when we're going forward, and especially when we leave the Bitcoin world and go to programmable blockchains. And that's something called Bitcoin scripts. So I have to kind of confess that I lied to you a little bit when I was telling you how the transactions work. So as I told you before, every transaction in Bitcoin has a bunch of inputs and a bunch of outputs, right? And basically what I said before was that every output is just the public key or address of a recipient. But in the real world, in Bitcoin, this is a bit more complicated. So it's not just that every output has a public key. Actually, every output can have a script. Okay. And the idea is that the script that you put in this output, it's written in a very limited language called the Bitcoin scripting language. And it basically sets down the conditions for spending this particular output. Okay? And of course, the most common condition is that I want a signature from someone with this particular public key. And that's why initially I just kind of lied to you and said it just has a public key of the recipient. But actually you can have more general scripts. So you can say that, for example, I want the signature of 2 different people with these 2 different public keys in order to spend this output. And then similarly, every input, I previously told you that in order to spend this, in order to have this input in this transaction, you need a signature that shows that you actually own it. But actually here you also need, well, let's say an input to a script, but or parameters for a script, or actually another script. And the idea is that you have to prove the requirements, prove that you satisfy the requirements for spending this. Okay? So let's say parameters that show you satisfy the requirements. So let me give you an example of this. So I might have a transaction 0, that has, let's say, 5 Bitcoins here, and then creates an output, and this is also 5 Bitcoins. But the condition for spending these 5 Bitcoins can be more complicated. Instead of saying that I just need a signature from the new owner, I can say the condition is that I need signatures from 2 people. So signatures from, for example, both Alice and Bob. And of course, here I'm using names, but in practice, these are just public keys or hashes of public keys. So these are addresses or identities or hashes of public keys. Okay? So if this happens, if I say the condition for spending these 5 Bitcoins is to have signatures from both Alice and Bob, then later on when I create another transaction, sorry, something is wrong with my board. Okay. So then later on when I create another transaction, let's say transaction 1, and this transaction wants to use those 5 Bitcoins of transaction 0 as one of its inputs, then it will need to satisfy this condition. And in order satisfying this condition means giving signatures from both Alice and Bob. Okay. So now just to spend this single output as the input in your next transaction, you need signatures from both Alice and Bob. Otherwise, this transaction will be invalid. Okay, so let me write it like this. This thing is signed by both Alice and Bob. Okay, so generally speaking, every output has some condition, and that condition is in a scripting language, so we call it a script. Sorry. Okay, and every input also has a proof, let's say, that the condition is satisfied. For example, in this case, the proof is the signatures by both Alice and Bob. And actually, this proof is also a script in the same language. So Bitcoin has the same language for writing the conditions and the proofs. And you can look it up and learn it if you want to. It's a very limited language. It can do only a few different things. So it can do very limited operations. For example, it can check signatures. This is the most common operation. The most common operation, the most common condition is that I need a signature from a particular person, a particular public key. And the most common proof is to give that signature. Okay, so that's why I was basically not talking about scripts at all when I was presenting to you how the transactions work. And I was just saying that, okay, they send money from one person or a group of people to another group of people. Okay, but there are also some other things there that are really nice. So again, one of the nice things that you can write in this language is this idea of multisig or multisignature, which means that you require signatures from several different people. Or maybe you can say, I require signatures from 2 of these 3 people. There are many different things that you can write in this script, but I have to tell you that the script is really limited, and actually it doesn't have any way of creating loops or recursion or functions or any fancy thing like that. So it's not really a nice programming language. It's just a very limited scripting language. And one of the really important issues here is that every script must terminate. So every script terminates, and actually it terminates very fast. So because there is, as I told you before, there is a bound on the size of a block. So every block can be 10 to the power of 6 bytes. If your block can be 10 to the power of 6 bytes at most, that means your transaction can be at most 10 to the power of 6 bytes. Okay, of course, a little bit less because you also need block headers. So that means that your script cannot be too long. And since your script cannot have loops or recursion or anything like that, it's just a straight line program. So it will easily terminate, and it will terminate in a very short time. And that's really important because, of course, everyone on the network has to run all of these scripts, because that's the only way that they can figure out if a transaction is valid or not. So if you remember when I was talking about the validity of transactions, I said one of the conditions is that they have to have the right signatures. But now, instead of that, we have to say that they have to have the right proofs, the right scripts for every input, showing that the conditions for spending that particular output as an input in this transaction are satisfied. So because every node has to check that when they want to check, for example, for validity of a transaction to add it to their mempool and propagate it further, or when they want to check the validity of a block that contains this transaction, then these scripts should be really short and easy to validate. And actually, one weird quirk of Bitcoin that has happened over the time is that these days miners have a whitelist of transactions, of scripts. Sorry, miners have a whitelist of scripts. So what that means is that if you write a script that is not on the whitelist, then the miners will simply not mine it and will consider your transaction to be invalid, even though it's not invalid according to Bitcoin rules. And again, the most common scripts are just the script that asks for a particular signature or the script that asks for signatures from several different addresses. Okay, so this is all for today. And this is the end of this session, so you guys can leave now, but I will stay and answer any questions that are in the chat. Okay. I have to go back to sharing because some of these questions require this. Okay, so one question here is, how can both TX and TX prime be placed in the chain in case of a fork? Shouldn't the network already have agreed which one is correct, given the fact that Alice and Bob have multiple nodes? Well, not necessarily. Again, this thing can happen. It can happen that half of the network thinks that, or well, some portion of the network thinks that TX is valid and some other portion thinks that TX prime is valid. And then it really depends on the point of view of the miners. So you might have a miner that thinks TX is valid or prefers to think TX is valid and include it in their block. And you might have another miner that prefers TX prime. And if that happens, then you can have a fork like this. If you get unlucky and both of the miners find a valid block at approximately the same time, you can have a fork like this when one miner puts TX prime in the block and the other one put TX. But what's important is that in the end, we will reach consensus, right? So in the end, one of these forks, one of these two chains will become longer, and then it will become the consensus chain. So in the consensus chain, there will always be only one of these two. In the consensus chain, we will never have a double spent transaction. Okay. So there is a question about resubmitting homework 1. So right now we are in the process of giving feedback to all the submissions. I think we are half done. As soon as everyone receives feedback, we will open the homework for resubmission, and then you will have 10 days to resubmit. Okay, and the next question is about grading of homework 1. No, it's not finished yet. There are so many of you, it takes time. So someone says, I thought we still had more time for final submission. I don't know what that means. So the deadline for homework 1 has already passed. You might get to resubmit if you submitted something and didn't get full marks, but if you didn't submit anything, you cannot resubmit. Okay. So another question is, in homework 2, what is the meaning of spending a coin that does not belong to the central bank? Okay, so the coins have owners, right? So a coin can belong to a particular public key, and maybe that public key is not under the control of the central bank. So let's say it's Alice's coin, it's not the central bank's coin. So can the central bank spend the coin even though they're not the owners of it? Can they spend it even though they don't have the secret key that corresponds to the public key of the owner of that coin. Okay. Okay, so there is another question about discussing the problems with classmates. So generally, the rule that we have about homeworks is that you are allowed to discuss them with your classmates, but there are two limitations to this. The first limitation is that you have to write your own answers. So if you submit answers that are clearly just copies of each other, we will disqualify both of them. And the second limitation is that after you get feedback from us, you can no longer discuss with classmates because that's cheating, right? You already have feedback from us, so you know the right answers. So another question is, does that mean the central bank can have the secret keys of the users? No, so the central bank does not have the secret keys of the users, but what that homework asks you is whether the central bank can spend the money anyway without having those secret keys. So another question is, I have received the feedback so I can resubmit in the future, right? In most cases, yes. I think your feedback should tell you if you can resubmit or not. Generally, you cannot resubmit if you got full marks or if you didn't submit a particular exercise. So in most cases, the answer is yes, you can resubmit. Okay, any other questions? So another question is, after we add the transaction to blockchain, how can we verify it? How can we check for it? Well, as a node, you are seeing all these blocks, right? And for every block that is propagated, its Merkle tree of transactions is also propagated. So you can just see every block and you can see all the transactions that are in that block. So you can just check if a particular transaction that you're looking for is actually in that block or not. And actually, most end users just use APIs that some websites provide, for example, blockchain.com. Yes, there is also a question that only the root is added in the chain. This is a recurring question, yes. So only the Merkle root is added on the chain, but the whole Merkle tree is propagated on the network. So if you are a node on the network, you will see that this particular Merkle root got added to the chain, but you also see the whole tree. So you don't have to add the whole tree to the chain because the Merkle root uniquely determines the tree. But every node on the network knows about the tree. So every node knows about all the transactions that are in that block. Okay. Great. So I think those were all the questions. I'll see you all in the next session.